So I'll go through this real quick. Two people, virtually the same question. Michael Knopf said, even though those pencil-neck scientists tell us that FTL, faster than light travel, is impossible, as a lifelong sci-fi nerd, I believe it would be way super cool if it weren't. Should I hold on to this hope despite all the evidence to the contrary? And Matthew Lloyd says, I wish we could bend space-time or create some other form of interstellar travel during my lifetime. Possible, probable, question mark. In your lifetime, Matthew, I would say the chance of that's approaching 0. And Michael, I'll tell you my little story about FTL. I was, like everybody else, science fiction nerd. I thought FTL was just the next thing, right? You just put enough power behind something, off you go. Einstein's got a lot to say about that, and none of it's good. What Einstein taketh away, he also giveth. Needless to say, I won't waste a lot of time with this. But basically, while Einstein says nothing can travel faster than the speed of light, he also says that as you get close to the speed of light, time slows down. So if you're on a spaceship, technically speaking, without violating any laws of physics, if you had enough energy, and it would take an awful lot of energy, but if you could get your spaceship up to 90, 95%, 96% of the speed of light, time slows down enough for you so that interstellar space travel is in fact possible. It's just you don't get to come home to the home you left. The home you come back to is 50 years, 100 years, 200 years in the past. Now that to me is interesting, actually. The science fiction universe I'm working on in the distant future, I spent a lot of time on this when I was in my 30s. And once again, it's laziness. But if you think about it, if you grant that there's no such thing as faster than light travel, and you send a group out in a ship that's traveling at 98% of the speed of light, let's say, and let's say that they live in 2100, and off they go to Tau Ceti. It takes them 12 years at the speed of light, so let's say it takes them 20 years to get there, 16 years, acceleration, deceleration, so on. And then they come back, and it's 30 years later, it's 40 years later. Meanwhile, other groups have gone. And what it basically means is, in a universe that respected the laws, this would be interesting. You would have cohorts of people all throughout the galaxy, and I don't know whether they'd mix or not, because the best way to think of it would be, here I am, I'm about to go to the shopping mall, and in come people from, Spanish conquistadors from 1590, and they just got off of their spaceship, and they're 400 years out of date from where I am. What do we do? Cool. Anyway, the question of faster than light travel, I wanted it forever, and then I went through a very long period, which still pretty much owns me, when I said, even the theoretical stuff, requires, you hear things like it would require as much energy as, as the output of a galaxy or stuff. I don't think we're done with multidimensional physics. I think we're just getting started with multidimensional physics. So far, the news is very, very bad. Einstein says it's not possible. The wormhole thing is a problem because, bending space and time and so on, and gravity and all this other stuff, it seems like it requires huge amounts of energy. And the reason I say it requires huge amount of energy is if it takes mass to bend space-time, right? If a planet bends space-time, the gravity field of a planet is curved space-time in the fourth dimension, and a black hole is a super dense particle of mass that's really bending space-time. The problem with that is that mass is essentially, a good way to think of mass is condensed energy. There's just so much energy in matter. If you take a little ball of plutonium this big, smack it together hard enough, and that's a reaction that converts, what is it, 8% of the total energy available? Less, maybe more, 16, something like that. Boom. There's a lot of energy in matter. And if you have a little tiny p of energy and a little p of matter and a little p of antimatter, and you put the two together, you're gonna get quite a flash for your camera. So again, the energy requirements seem very high. But theoretically, since I was a true believer in no faster than light travel, since then I'm seeing little signs, experimental signs that are showing me maybe. I mentioned this before. I mentioned it again. If you're interested in this kind of thing, go and look for a free software called Celestia. It's terrific. It's a solar system. It's not a simulator. I guess it's a simulator. It's the entire solar system. It's free, downloadable for free on the Mac and the PC. And all the planets are to scale, and all the orbits are to scale, and everything's to scale, and it's great. And on the Mac version, at least, I don't know if they've upgraded the PC version, but on the Mac version, you can set your speed. And so I traveled through the solar system at the speed of light. And, buddy, the speed of light is slow. It's slow. I mean, you see the Earth and the Moon, and they just come in, and then yeah, they blow by pretty quick. But I mean, you can tell. It took 8 minutes to get to the Earth from the sun. Once you enter the Jovian system, if you turn it on with all the orbits are lit up, you enter the Jovian system at the speed of light from getting inside the outer moon, and it takes you something like, I don't know, 20 minutes, 15, 20 minutes to get through this thing. You see these things peeling away, and Jupiter's there, and then the Galilean moons are there, and it's coming. You'd think it'd be like, no. If you're interested in this kind of thing, get Celestia just so you can see how slow the speed of light actually is. The speed of light is actually pretty slow. And needless to say, you think, man, okay, let's go to Celestia. We're going to hit the speed of light, and we're going to watch the stars do their dilation thing. No, you're out of your mind. You're moving at the speed of light, man. You're going to have to sit in front of your computer for 4.5 years before you see the first star show up on your doorstep. 4.5 years. So in order to get the Star Trek dilation effect, you go to 100 times the speed of light. You still can't see it. And I think you have to go to like kiloparsecs a second before you begin to see this thing. So, anyway, so much for the speed of light question.